In our today's lesson, we will focus on binomial probability distribution. So binomial probability distribution is a discrete probability distribution, and we will see how we can apply the binomial probability distribution to many real world problem and get the solution of this problem. In our today's lesson, our focus is to learn to identify the binomial experiment, like in which situation we should use binomial probability distribution. We will learn that. Then to solve the binomial probability distribution problem, we have two ways. We can directly use the binomial probability distribution formula to solve this problem. We'll learn how can do that, and another alternative way is to use the binomial probability distribution table to solve the same problem, and we will also see how we can use binomial table to solve the problem. And we will see like our many of the real world problem is can be solved very easily by using the binomial probability distribution, and we will see how we can do that in this lesson. Let's talk about some of the key feature of the binomial probability distribution. So for the binomial probability distribution, the number of trials must be fixed, and we denote that by n, and that must be predetermined and constant. As for example, if we throw a coin 10 times, then the number of trial is 10, therefore n equal to 10, and the trials must be independent. So if we throw the coin 10 times, then each of the throw must be independent, and we have to repeat the process under identical condition. And we will always have two outcomes for a binomial probability distribution, and we call that failure or success. As for example, if we throw a coin, then our either head or tail might appear, right? And we can denote any of the head or tail as success and the other as failure. We have talked about the key features of the binomial probability distribution. Now let's talk about some of the notation that we use, and some of the concept that we usually use for the binomial probability distribution. As for example, that I was saying is that the probability for the binomial probability distribution must be always constant, and we denote the probability of success with P, and we denote the probability of failure as Q. Then the relationship is that like P and Q, that means the probability of success plus probability of failure must be equal to 1, and therefore Q equal to 1 minus P. That means the probability of failure must be 1 minus probability of success. And for the binomial probability distribution, we use this formula where PR, that means like probability that there will be R success out of n trial. So if we throw the say coin 10 times, then what is the probability that 5 head will appear? So in that case, then n equal to 10 and R equal to 5, right? So how many success is denoted by R, and how many trials is denoted by n. And the formula that we use for the probability for the binomial probability distribution is like that. We'll elaborate on that later. So let's now talk about the key component of the binomial probability distribution formula. So this is the binomial distribution formula. So that basically tell us what is the probability that there will be R success out of n trials. So here, like n is the number of trials, n is the number of trials. In the formula you see n, this is the number of trials, and R is the number of success out of n trials. So R is the number of success out of n trials, and then P is the probability of success in each trial, and this P is basically constant for all the trial. P cannot change, P will be identical, right? And then Q is the probability of failure, which is basically 1 minus probability of success. So Q is 1 minus P. Then this part of the formula, which is basically known as binomial coefficients. So these are the components of the binomial probability distribution formula. So in the next couple of slides, we will elaborate on that, and with a real life example, we will see how we can apply binomial probability distribution formula there and get the solution for the problem. As I was saying, like this part of the binomial probability distribution formula is basically known as binomial coefficient, which is basically n chose r. We read it as n chose r in combination r, and you already know, like if you expand that, then which is basically n factorial over r factorial times n minus r factorial, right? Now let us use an example and try to see whether this experiment satisfy the criteria for binomial probability distribution. So here we have one student who is flipping a coin 5 times, and he want to find the probability of getting exactly 3 head. So now, does this coin flipping scenario meet the criteria of the binomial experiment? We'll see that in the next slide. So let's talk about the components of the example that we have just mentioned. So the coin is flipped 5 times. So here then the number of trials would be 5, and each of the flip is basically independent, right? The outcome of on trial doesn't depend on other, and in that case for a coin flip we have two outcomes like head or tail, and we have the constant probability because the probability of getting head always remains 0.5, right? We have 50% chance of getting a head or 50% chance of getting a tail, and then we want to find the probability of exactly r equal to 3 heads out of five flips, right? So here in that case our r is equal to 3. So it appears like it satisfies the criteria of the binomial probability distribution, right? In fact it does. So now in the next slide we will see how we can use binomial probability distribution formula to get the solution for this problem. So for the problem, we had the student has flipped the coin 5 times, and he is interested to know what is the probability that he will exactly get 3 heads. Therefore in that case our number of trials is 5, and the probability of success is 0.5, right? Because if you flip a coin, then the probability of head is 0.5, and the number of success the student is interested is to know whether he will get 3 hits or not. Therefore in that case the r equal to 3, and now we know that the binomial probability distribution formula is like that, right? Is like that. So in that case now we have, for this formula we have n which is 5, we have r which is 3, and we have p which is 0.5, and we also have the q. If p is 0.5, then q is basically 1 minus p, which is also 0.5, right? So now we have all the component for this formula, and we can calculate this probability, right? So if you just plug in this value in this formula, we finally get that. Then we can calculate this part of this formula. So first we can calculate the value for the binomial coefficient. So if you calculate the value for the binomial coefficient, which is 10 here, and then we have this part which is probability of success like 0.5 over r in that case is 3. So this part that give us this value, and then for this part we have this value, and finally if you take like all of these into consideration, then you get the value you get the probability 0.3125. And what does that mean? That means the probability of getting exactly 3 head in 5 flip is 31.25%, right? That means if you flip the coin 5 times, then the probability that you will exactly get 3 heads out of the 5 trial is 31.25%. I think now it is clear to all of you like how we can solve a binomial probability distribution, right? Now let's see if we are asked to calculate like what is the probability of getting more than 3 heads out of the 5 coin flips. We can basically do that, right? So here we are asked to calculate probability that there will be more than 3 heads. That means there will be like 4 head or 5 head out of the 5 trials, right? And then that means like we need to calculate like two probabilities, probability that there will be 4 head or there will be 5 head. Now let's see how we can do that. So we'll just plug in this value in the previous formula, and in that case then we'll have n equal to 5, r equal to 4, and p and q will be the same, right? And in that case, the n equal to 5 and r equal to 5, and all other things would be the same. Then for getting this probability, what you have to do, you have to just sum of these two probabilities, right? And if we take the sum of these two probabilities, the value is that. What does that mean? That means the probability that getting more than 3 heads in 5 coin flip is 18.75%, right? So if you flip the coin 5 times, then the probability that you will get more than 3 heads is 18.75%. Let's look into another problem and see whether in that case we can use binomial probability distribution. So here consider a basketball player who makes 80% of their free throws successfully. If the player attempts 10 free throw, we want to find the probability of them making exactly 7 shots. So in that case, how many throw he is attempting? He is attempting 10 throw. Therefore there will be like number of trials would be 10, and there are two possible outcomes. Either he makes the shot successfully, or he failed to make the shot successfully, right? And then the probability is also constant. The probability that he will make a successful hit is with 80%. That means p equal to 0.8, and therefore the q will be like 1 minus p, which is then 0.2. And each trial is independent in that case, like each free throw attempt is independent. The outcome of one shot doesn't influence the outcome of the other another shot. And in that case it is a counting problem. We are interested in the number of successful shot, especially we want to check like what is the probability that he will make exactly 7 shots successfully, right? So in the next slide we'll see how we can solve this problem with a binomial probability distribution. In the previous slide we have discussed like different components of this problem, and we have checked that this problem basically satisfied the condition for the binomial probability distribution. And in that case our number of trials was 10, and we are interested to see out of the 10 shots what is the possibility that he will make 7 successful shots, right? So then our r in that case is 7, and the probability of success was 0.8. Therefore the probability of failure would be q would be 0.2, right? So we can just plug in these values in this formula, like in the binomial probability distribution formula, in this formula, and that basically give us this number, right? So this is the probability that he will make exactly 7 successful shots. And if you plug in this value, and after the final calculation, and we can calculate like each part separately, and here we have the calculation for each part. This is for the binomial coefficient parts. Then for this part we have this value, and for this part we have this value, and finally after the final calculation the probability that we get is 0.201. That means the probability that the player will make 7 shots successfully is about 20%, right? So the probability that out of the 10 throw he will make 7 exactly 7 successful shot is with probability 20%, right? I think now it is clear to all of you like how we can apply binomial probability distribution to get the solution for different real world problem, right? Let us look into another problem. So one survey revealed that 59% of the people are concerned about their confidentiality of their information online. So now our question is, for a random sample of 10 people, what is the probability that exactly 6 are concerned about online privacy? So in that case, our probability is 59%. That means P equal to 0.59, and N is 10 because in our sample, in our random sample, we have 10 people, and R is R equal to 6 in that case, right? Now in the next slide, we will see how we can solve this problem using binomial probability distribution. So here, as I was saying, in that case, n equal to 2, n equal to 10, because we have a sample of 10 people, and then P equal to 59%, that means P equal to 0.59, and Q equal to 1 minus P, that means Q equal to 0.41, right? And then R equal to 6, like exactly how many are concerned, right? So now we'll see how, using this information, we can solve this problem using a binomial probability distribution. So now we have all the components for a binomial probability distribution, and we can just plug in the value in the binomial probability distribution formula. So in that case, we are interested to see exactly 6 of them are concerned about their privacy online, right? Then our n, in that case, number of trial, that means number of trial in that case was 10, and R equal to 6, and the probability of success in that case was P equal to 0.59 and Q equal to 0.41, right? So if you plug in all the values in the binomial probability distribution formula, then we basically get that. And the coefficient part, the value for the coefficient part is 210, and this part, the value for this is approximately 0.0424, and the value for this part is approximately 0.0283, right? And then after the final calculation, the value we get is approximately 0.25. That means there is a 25% chance that exactly 6 of the people out of the 10 are concerned about their privacy online, right? So here, let's look into another problem. So a biologist plants a new variety of tomato seeds, and the germination rate of the tomato seeds is 70%, and the biologist planted exactly 6 seed, and he's interested to know the following probabilities. What is the probability that exactly 4 seeds will germinate, and what is the probability that at least 4 seeds will germinate? So for this problem, our number of trial is 6, so n equal to 6, and then P here, probability of success is 70%, that means P equal to 0.70, and Q would be like 30%, right? So Q would be like 0.30, and R for the first problem is 4, so number of successes interested is like 4, right? So we'll see like how we can calculate this probability. So now we'll solve this problem using a binomial probability distribution table. So earlier we have solved some binomial problem which is using the binomial distribution formula directly. So in that case, we'll be using binomial probability distribution table. So for different n, we have different binomial table. So this table is for n equal to 6. So this table is for n equal to 6. Then we have different value of R in this column, and we have different value of probability, different value of the probability P in this row, right? And we are particularly interested for R equal to 4, like exactly like 4 seeds germinated out of the 6, right? And with the probability in that case was the germination rate was 70%, right? So we are basically interested with this probability, and for R value equal to 4, and the corresponding probability in that case is this, right? 0.324. So the probability that exactly 4 seed will germinate out of the 6 is with probability 0.324. That means there is 32.4% chance that exactly 4 seed will germinate out of the 6, right? Now our next question was at least 4. What is the probability that at least 4 seeds will germinate? So to get at least 4 seeds will germinate basically means that like the number of germination successful germination has to be 4 or 5 or 6, right? So yeah, so therefore the probability that more than at least 4 seeds will germinate is basically same as that, right? Probability of 4 germination plus probability that 5 germination plus probability of 6 germination. Now we'll see how we can use the binomial table to solve this problem. Now for this problem we are interested to know like there will be at least 4 germination. That means there could be like 4, 5 or 6 germination, right? Since we have total like 6 seeds, therefore, and we are interested for at least 4 germination, so we are interested basically for probability that R will be 4, 5 or 6, right? So that means, and our probability was like probability of germination was 70%. So here then our R is 4, 5 and 4, 5 and 6. So therefore we are interested for this, right? And we have to, and we have the corresponding probabilities here. So what we have to do to get the final probabilities, we have to basically take the sum of all of this probability, and that will finally give us the probability that there will be at least 4 germination out of the 6 seeds, and we will do that in the next slide. So from the previous slide we have seen like the probability that there will be 4 germination is that, and the probability that there will be 5 germination is that, and so on. And if we take the sum of all of these, that basically give us this value. So that means like there is at least 4 germination will happen is with probability 0.745, or in other words we can say like there is 74.5% chance that at least 4 of the seed will germinate, right? Now let's talk about a very important concept in probability, which is the complement rule. So imagine for a binomial experiment we have 7 number of trials. Therefore the value for the R could be like 0, 1, 2, 3, 4, 5, 6 and 7, right? Because the success cannot exceed the number of trials. So the number of success could be like 0, 1, 2, 3, 4, 5 or 6. And for any probability distribution, the sum of all of this probability would always be 1, right? So now say if you are asked what is the probability that at least there will be one success, that means this, right? Probability that R greater than or equal to 1. So now let's see what is basically asked here. So it basically asked you those probabilities, right? Like what is the value for those probabilities. Now to calculate this, you basically need all of these probabilities, and that is a long list, right? So you have to do a lot of work. But what we can do instead is that's basically same as 1 minus probability of 0, right? If we just take these to the right hand side, or we basically subtract like probability of 0 from both sides, then for all of these basically we get 1 minus probability that R will be 0, right? So this is the complement rule. And similarly, like say if you are asked what is the probability that R less than 6, then what does that mean? R less than 6, that means you are interested for all of this probability. You have to take the sum for all of these probabilities, right? Which is same as like for these, so this sum of all of these is basically equal to 1 minus probability of 6 minus probability of 7. So instead of like doing all of this calculation, what you can do, then you can just plug in the value for these two and get this probability, right? Similarly, if you are interested for probability that r will be less than or equal to 6, then you are interested for all of this probability. And alternatively, what you can do, it basically have to then do that 1 2 3 4 5 6 7 times, but instead what you can do, you can just convert this problem to the complement problem. That means all of these equal to just 1 minus probability of 7. So now only just plug in this value in your probability distribution, you can get the same value, right? So this is really very important, especially when you have a long list of r. In that case, applying the probability complement rule, you can solve the problem very easily. So finally, let's look back what we have learned in our lesson today. So we have discussed about the criteria for a binomial distribution, like what are the criteria for a binomial distribution, then how we can apply the binomial distribution formula to solve the problem, and alternatively we can also use the binomial probability distribution table to solve the same problem, right? And we have also seen like how we can solve many real world problem using the binomial distribution, right? Thank you everyone, see you in the next class.